All right, in this video, we'll be going over work, energy, and power. Now, we'll mainly be going over kinetic and potential energy, because I think that's what's covered most on the FE. But work and power have the same units, and they're kind of the same thing, just used a little bit differently in the real world. But yeah, we're just going to kind of be going over kinetic and potential energy in this video and in the quizzes and stuff. If you do want me to do more on work and power, let me know, and I'll put a video together and we can go over that stuff. But let's go ahead, dive right in. Let's talk about kinetic energy. So one thing you need to know is the difference between translation and rotation. And each of these comes with their own equation for kinetic energy. So translation would just be taking an object and translating it in space, whereas rotation would be taking an object and just rotating it about some axis, and it's not really actually moving in space. That's translation. Now, you actually can have a combination of both of these, where you could have some sort of disk that's rolling along the ground, but it's also moving that way as it rotates. So you would combine translation and rotation. So the equation for translation is 1/2 mv squared, where m is mass and v is velocity. And for rotation, it's a little bit more complicated. You're going to get 1/2 IC omega squared, where IC is the moment of inertia of that object about its centroid, and omega is the angular velocity. Of that object. So let's go ahead and just look at translation for right now. If we had a 2 kilogram object moving at 10 meters per second, its kinetic energy would be 1/2 mv squared. And you just plug it into a calculator and you get 100. Now the units on this would be kilogram meter squared per second squared, which is actually a joule. All right, so we get 100 joules for that. But if we had an example where we had rotation and translation, say for example, we've got this disc here, and it's 1 kilogram. It's on some horizontal surface. And we know that angular velocity equals 3 radians per second. And we also know that the radius of this object is 1 meter. All right, so we would get our kinetic energy of being a combination of translation and rotation kinetic energy. So it'd be 1/2 mv squared plus 1/2 IC omega squared. So from this equation, we have this. So we need to go in and find IC and V. All right, so IC for a disk is actually 1/2 mr squared. So that's going to be 1/2 times 1 times 1 squared, so that's going to be 1/2. And V is actually equal to omega times R. So 3 radians per second times 1 meter. We're going to get 3 meters per second. All right, and then you can just go ahead and plug and chug. So we're going to get 1/2 times 1 times 3 squared plus 1/2 times 1/2 times 3 squared. You plug that all into a calculator, you're going to get 6.75 joules. All right, so go ahead and try a couple of these on your own. Let's say you've got a 1,000 kilogram object traveling at 30 meters per second. Find kinetic energy. And then also, if we've got um, 10 kilogram disc, has a radius of 0.5 meters, and it's also has a velocity of 20 meters per second. All right, find the total kinetic energy for that one as well. Pause the video, work those out on your own, check your solution with the PDF found below this video. And those are number 1 and number 2 on that PDF. Make sure you did them right. Okay, so just one more thing to point out with rotational kinetic energy is that if you had some sort of axis here and you had a bar attached there, and then at the end of this bar you had some sort of disc, right? So if this bar was rotating about this axis, and this is also, the disc is also rotating about that axis, you kind of have two different forms of rotational kinetic energy. So you just go ahead and add both of those up. So in reality, you can have kinetic energy, if you had rotation about all 3 axes, you would have 1/2 Ix omega x squared plus 1/2 Iy omega y squared plus 1/2 Iz omega z squared. All right, so you just do the rotation about each axis and then add it up. In this case, we would only have rotation about 2 axes, so one of these would go to 0. But if you did have rotation about all 3, then you just add them up, all right? All right, let's talk about potential energy. All right, so if you were standing on a building and you were holding some sort of object over that ledge, this object is not moving, and so it doesn't have kinetic energy yet, but if you were to drop it, it would have kinetic energy. So because it's not moving yet, that's why we call it potential energy, because it has the potential to gain energy. All right, now this height would be h. The object obviously has a mass, and so the potential energy for an object is going to be mgh. So mass times gravity times height. All right, so if we had a 1 kilogram object and this was 1 meter, our potential energy would be 1 kilogram times gravity, 9.81 meters per second squared, times 1 meter. We would get 9.81 joules of potential energy. All right, now another thing to point out is that springs also have potential energy. So if you had a spring and it was just at rest, it has no potential energy. But if you were to stretch this out or compress it, then you have potential energy gaining up, because as soon as you let go of that spring, it would bounce back to its neutral position. So the potential energy of a spring is going to be 1/2 kx squared, where k is your spring constant, and x is your distance that you compressed it, or your distance that you stretched it. So just that distance from the neutral position that your spring is at. So, for example, if we had a spring that had a spring constant of 100 newtons per meter, and we stretched it 0.1 meters from its neutral position, our potential energy would be 1/2 100 newtons per meter times 0.1 meter squared, and we would get 0.5 joules of potential energy in that spring. All right, so go ahead now and try on your own. If you had a spring, so the spring constant 100 newtons per meter, and you stretched that spring 5 centimeters, what would the potential energy of that be? And then also, if you had a 10-meter building, and a 5-kilogram ball that was hanging over the edge, what would the potential energy of that be? All right, pause the video, work those out, check your solution with number 3 on the PDF. All right, and then finally, the last thing we're going to go over is the conservation of energy. So energy is going to be conserved in these situations. So you can actually take the potential energy of the object at position 2 plus its potential energy at position 2, set it equal to kinetic energy at position 1 plus potential energy at position 1. So if we had let's see. If we had a 1 kilogram object and it was 1 meter high, what would its velocity be when it hits the ground? So we can just take this, so we can call this position 1, and the ground is being position 2. So at position 2, the kinetic energy is going to be 1/2 mv squared. Now the potential energy, now it's on the ground, is going to be 0 because h is 0 at the ground. And then kinetic energy at 1, we're holding it, so there is no kinetic energy, but the potential energy is going to be mgh. So we're going to get 1/2 times 1 times v squared equals 1 times 9.81 times 1. And if you solve that all out, you're going to get a velocity of 4.2 meters per second when it hits the ground. All right, so go ahead and try one of these on your own. Let's see, let's do... Uh, 30 meters high, and it's a 2 kilogram ball, and we want to find velocity when it hits the ground. All right, let's go ahead and work that out and then check your solution with the PDF. This is number 4 on that PDF. And that covers it for energy.